Okay, question 12. Diagram below shows a diagram for the mass spectrometer. It gives us the velocity selector, the field strength of velocity selector, and the electric field strength. So that's key. First question though, interesting, define the unit for magnetic flux density, the Tesla. So how do you go about defining a Tesla? Well, you have to do it from this bit here, F equals BIL, and it's got to read something along the lines of the field strength that gives rise to a force of 1 Newton per meter in a conductor carrying a current of 1 amp, and then that's got to be the first mark, and then for the second mark, that is perpendicular to the direction of the field. Okay. Alright, once we've done that, next up, show the velocity selected is independent of the charge on an ion. Well, it's this old application of these two equations. Force equals BQV, that is the force on a charged particle, and F equals EQ, that is a charge on a particle in an electric field. If it's going in a straight line, then these two forces will be balanced. Okay, so that's equal to that. Once we've got that, we can say, well, divide through by Q, and we find that BV equals E. Therefore, the velocity is E over B. And really, you can get that far, and you're probably fine there. But just a really good bit of advice in exams to say, so therefore, velocity is independent of charge. Just say what that shows. Okay, next up, show the velocity selected is about 140 kilometers per second. Well, if the V is E over B, they've told us the electric field is 20,000 volts per meter, and the magnetic field strength is 0.14. When you divide that by that, you get 142,857 meters per second, which is roughly 140,000 or 140 kilometers per second. Right. Next up, sample of nickel is analysed in the spectrometer. The two most abundant isotopes are 58 and 60. Okay, that's the mass of them. They each carry a single charge of plus 1.6 times 10 to the 19. So they've got basically their single plus 1 ion. Now, the N52 Ni ion strikes the plate 0.28 from the point at which the ion beam enters the separator. There it is. So it's going like that and it's one of these two. We don't know which one it is yet, but it's one of these two. Okie dokie. So, back to this statement here. Force is BQV, which is equal to mv squared over r. That's the centripetal force. That's the force due to the charge, due to the interaction between the charged particle and the field. Of course, the V on both sides cancels out, and we can take the Q down there to get B equals mv squared divided by QR. Once you've got that far, the rest's easy. You plug in the value for the mass, which is 58 times by 1.7 times 10 to the minus 20. That's the total mass of our ion. Times by the velocity. I decided to use the velocity that we calculated up there, which is 142,857, divided by the charge on the ion, which, as we just said, is 1.6. It's a single charge of 1.6 times 10 to the minus 19 coulombs. And the radius. Now here you've got to be careful because it says it strikes 0.28 meters. This distance here. That's this distance here is 0.28 meters, which means the radius is of course half of that. So you've got to divide that bit by 2, so we get the radius. And when you do that, it comes to 0.629 Tesla. Well, that's what I make it anyway. Okie dokie. And then the next thing to say is the separation. It wants you to find out the separation of the positions where the two isotopes hit the photographic plate. So, straightforwardly here, we go back to this thing here. Just keep going back to this basically. F equals BQV equals mv squared over r. Again, the V cancels out with that one there. And then I'm just going to rearrange this to make the radius the subject. Now, once we've done that, it's mv over bq. And the new mass, okay, the first one it asked us about was the 5828 nickel. Now it wants to know where the separation between that and the 60. So we put in a different mass, which is 60 times 1.7 times 10 to the minus 27. That's the mass. Sticking with the same velocity as before, set the magnetic field strength that we've just calculated from there. Okay, we can plug that into there, and the charge remains the same. When you do that, you get a radius of 0.145, which gives us a diameter of 0.29, and in the first instance, this one, it tells us that there for the first one was this one, which is 0.28, and we've now found our heavier one goes to there, which is 0.29. Okay, now that means the difference, they land 1 centimetre apart. And that is all there is to do for this bit.